Folks, I'm Mr. Pinola. Today I'm sitting on this stool and I'm going to ask you a couple questions about me while I sit. First off, am I accelerating? If you said no, you'd be correct. That's because my speed is not changing. Now, very clearly I'm at rest, so we knew I was accelerating by that. But the fact is that even if I was moving, as long as my speed is not changing, I'm not accelerating. And so as I sit here on this stool, even if I sat here all day, my speed would not change, and therefore I would not accelerate. So today we're going to take a look at the forces that act on objects that are either accelerating or not accelerating. Now, we've already talked about these a little bit during our introduction to this unit, but now we're going to go into a little bit more depth and practice making some diagrams that actually show the names, magnitudes, and directions of all the forces that are acting on different objects. Let's head to the whiteboard and take a look. Let's start off our work by doing a quick summary about what we know about objects that are accelerating and not accelerating. So I'll divide my board into two. And on the left side, I'll write down some information about objects that are accelerating. Remember, if you are accelerating, that means that your velocity is changing. So you could be accelerating if you are speeding up or if you are slowing down. You could also be accelerating if you're changing directions, but we're not going to specifically talk about that today. If you are not accelerating, you obviously could be at rest. Or in other words, not moving, just like I just was on the stool. But you also could be moving without changing your speed, meaning you could be moving at a constant speed. For example, a car driving along the highway at a constant 65 miles an hour, that car is not accelerating. It might be going very fast, but since it's moving at a constant speed, it's not accelerating. So hopefully you knew about these things already, that acceleration meant changing your speed and that not accelerating meant not changing your speed, even if you were moving. But now let's think about the forces that are associated with objects that are accelerating and not accelerating. So now let's take a look at the forces that act on objects that are accelerating and not accelerating. If an object is accelerating, that means the forces on the object are unbalanced. That means that there is more force going in one direction than in another direction. In other words, there would be a net force that acts on your objects. And so the diagram showing all the forces would have one side a little bit longer than another. If an object is not accelerating, then the forces on the object are balanced. That does not mean to say that there are no forces acting on the object. It just means that whatever forces act, those forces balance out. So let's see if we can apply this idea, the fact that if an object is accelerating and changing its speed, that it would have unbalanced forces. And if an object is not accelerating and not changing its speed, that it would have balanced forces. Let's take a look at some examples of that. So here I am again, sitting on the stool, not accelerating. Are the forces on me balanced or are they unbalanced? If you said balanced, you'd be correct. And so most people would look at me and say, Mr. Pinola, there are no forces acting on you. And that would not be true. There are forces acting on me. It's just that we know that those forces balance out. So, which forces are acting on me? Well, remember, a force is a push or a pull. There is something pulling me downwards, pulling me towards the center of the earth. If you said gravity, you'd be right. Gravity is a force that always pulls something straight downwards towards the center of the earth. Gravity never pulls something sideways. It never pulls something at an angle. Gravity always pulls straight downwards. And so right now, as I sit here, gravity is pulling me downwards towards the floor. But you might be saying to yourself, wait, if gravity is pulling him down, that would create an unbalanced force. And I would accelerate and slam into the floor and hurt my butt. But I'm not. So what is the other force acting up that works against gravity that's keeping me balanced? Well, there is a force from the stool. This stool needs to be strong in order to keep me from falling into the floor. So the stool provides an upward support force to counteract gravity. So if gravity pulls down on me with 500 newtons, the stool needs to push up with 500 newtons back. And that way I will stay at rest and not start accelerating towards the floor. So welcome back to the whiteboard. Now let's draw a diagram that show the forces that were acting on me as I sat in the stool. We're going to diagram all of the forces in a diagram that is called a free body diagram. A free body diagram, which you may see abbreviated sometimes as FBD, for free body diagram. Essentially, a free body diagram is just a diagram that shows all the forces that are acting on an object. We've kind of started drawing these a little bit together already, back when we were practicing with net force. Now, in my free body diagram, I'm going to start out by drawing the object that the forces are acting on. In this case, me. Now, I don't look like a square, but we can just represent any object by just drawing a square. And so now let's draw the forces that are acting on me. We know that we just said gravity is a force that is acting straight downwards on me. And so I'm going to write F grav for the force of gravity pulling downwards. But remember, there was another force that was acting upwards. And that force has a name as well. I just called it in the last example a support force because it supports me from the ground. Some scientists also call it a normal force. Normal force might seem like a strange name, but it's just the scientific name for a support or a supporting force that could come from the stool or the ground that you're standing on or the seat you're sitting in. Notice also something else about my free body diagram. Do you see how I basically made the sizes of the forces the same? Well, that's important. And that's because we knew that I was not accelerating. And so the amount of gravity that was acting on me was perfectly balanced by the amount of normal force. If the stool couldn't put in enough normal force to keep me upright, then normal force would be shorter than the force of gravity. So to show a bigger force, I would draw a longer line. And since I drew these two lines the same length, I'm showing that they are both equal amounts of force and that the forces on me are balanced. They cancel out. Now let's take a look at another example, and an example that we're going to make a free body diagram of. Here is a heavy plastic container, and I'm going to push this container along the floor. I'd like you to take a look and watch the container as I push it. Did you notice that the container was moving at constant speed? It wasn't speeding up and it wasn't slowing down. Let me show that to you one more time. So we're going to start with the container here, and I'm going to push it at constant speed. Let's now go back to our whiteboard and see if we can draw a free body diagram for the plastic container while it moved across the floor. So let's start our free body diagram just as we normally would. We're going to draw a square to represent the object. In this case, the square kind of looks like the crate itself. It's a big boxy type object. And let's draw the forces that are acting on this container. Now, you might have noticed in our video showing the crate moving, that the crate was moving to the right. And so I'm going to draw a force going to the right. I'm going to call that my applied force. Applied force is like any force that a human or an animal would push with. Like if I push my chair out of the way, or I push against the whiteboard, I am using an applied force. But even though it might look like that's the only force acting on the crate, there are actually quite a few other forces that would be acting on it. Remember, this crate was moving at constant speed. That means that the crate was not speeding up, not slowing down, and the forces on it should be balanced. So, if there is an applied force to the right, shouldn't there be another force going the exact opposite direction? That would be the same amount. Do you know what force that is? If you said friction, you'd be right. This is the force specifically of sliding friction. And that's because as the box moves across the ground, it is rubbing against the floor. And so it creates a little bit of friction, which is balanced with my applied force. So, looks like we've got our free body diagram complete. Not so fast. Even though this looks like it would satisfy what we asked for, we have shown a couple of forces acting on the box. We're showing that these forces balance because the box was moving at constant speed. There is still a couple other things that we have to consider. Does gravity act on my plastic container? You bet it does. Isn't gravity still pulling the plastic container straight down towards the center of the earth? So I have to draw the force of gravity in on my container. But if you've got a keen eye, you'll look at this and say, wait, Mr. Pinola, now the forces are unbalanced. The left and right forces have balanced, but there is clearly more force going down than there is going up. So, what is the name of the upward force that must balance with the force of gravity? Well, if you said the normal force or the support force, you would be correct. Because even though the crate is moving in the left-right direction across the floor is still pushing upwards to keep the crate from falling through the floor itself onto a lower level of our school building. So this is actually a correct free body diagram for a crate that is moving to the right at constant speed. Notice the left and right forces balance, as do the up and down forces. And that means that we have no acceleration at all. But what if we had a situation like this? That time, I pushed the crate to the right, but it was speeding up the whole time. How would we draw a free body diagram for that? Let's go to the whiteboard and have a look. Similar situation we just saw, but this time the box was accelerating. It was starting to speed up as it went to the right. So We'll draw my box again. And let's draw the forces acting on it. I was clearly pushing it to the right with an applied force. And since it was still moving across the ground, there was still sliding friction going the other way. However, do you remember that the box was speeding up? That means the forces have to be unbalanced. And that means, in this case, since it was speeding up, there was more force going to the right than there was to the left. And so, I'm going to draw a smaller amount of friction than applied force, because I'm going to show that I got it to speed up. In fact, I was pushing with so much force that my applied force was bigger than the force of friction, causing acceleration. Now, am I done with my free body diagram? No, I'm not. There is still the force of gravity that's definitely acting downwards. And there is still the normal force acting upwards. And those forces balance out up and down because the box wasn't shooting into the air and speeding up that way or speeding up as it fell through the ground, but it was speeding up to the right. And that's why I'm showing still my same forces, but the force to the right is a larger amount than the force would be to the left. So we're back now one more time with our crate. Let's look at one other example. This time I'm going to push the crate and let go. And I'd like you to have a watch at what happens. 3, 2, 1. Was this box accelerating? If you said yes, you'd be right. That's because the second it left my hand, it started slowing down until it came to rest. So let's go back to the whiteboard and draw a free body diagram for my box as it slowed down. So here's my box one more time. It was slowing down. So it was accelerating, which means the forces were unbalanced. But did you notice that once I let go of the box, I wasn't pushing it anymore? So I'm not going to draw any applied forces here. I am going to draw the force of friction, though, acting in the opposite direction of the way the box was moving. And I'm going to draw the force of gravity just like I normally would on pretty much any object. And I'm going to draw the normal force from the floor that's pushing upwards on it. Does this show unbalanced forces? It does. And that's because notice the force of friction is the only force acting left and right. It is not balanced by anything else. So this is a diagram that shows unbalanced forces, and it would make sense for an object that is moving to the right but slowing down. This object moving to the right but slowing down because friction is acting the other way. So very strange to think about, but notice the only direction in which there is no force is to the right. You don't always need a force in the direction the object's moving. This shows an object that was just already moving to the right and is slowing down due to the unbalancedness of the forces. Let's take a look at the free body diagram for one last object. That last object is not going to be me. It's not going to be the box that I was pushing across the floor. This time it'll be a regular piece of paper. Watch the motion of the piece of paper as I drop it. 3, 2, 1. I'll do that one more time from maybe a little higher up. 3, 2, 1. Did you notice that as the paper fell, it was falling at pretty much constant speed? Well, we can make a free body diagram that shows that. Here's our piece of paper. Let's think about the forces that are acting on it. And let's remember that it was moving at constant speed, which means that it was not accelerating. So we know that the force of gravity is definitely acting on my piece of paper, pulling it down. You might be now tempted to draw the normal force going up. But was this paper on the ground as it was falling? Was it sitting on a chair or in a stool? No, it wasn't. So even though objects moving across the ground or just sitting on the ground would have a normal or a supporting force, this piece of paper would not. And so the force of gravity would seem to be the only force acting on the piece of paper. But if that were the case, then wouldn't the piece of paper be speeding up as it fell? What is the other force that has to be acting upwards to make the forces balanced? Because remember, the piece of paper was moving at constant speed. It was not accelerating. Well, this force is a force that's going against the motion of the object. It's a type of friction, but it's a very specific type of friction. Do you know which one? It's specifically fluid friction, which we're going to call air resistance. So this piece of paper was falling at constant speed because the force of air resistance acting upwards on it must have perfectly balanced the force of gravity. And so that's kind of weird to think about. Something could be falling through the air and not speeding up. And that's because the air resistance kept getting bigger and bigger and bigger until it balanced out with the force of gravity. There's a specific scientific name for this. It's called terminal velocity. As an object falls through the air, it gets faster and faster and faster. And so as we knew from our classwork the other day, as you get faster, the air resistance that acts on you gets bigger and bigger. Eventually, when the amount of air resistance equals the force of gravity, then the object has reached terminal velocity. And that means that the force is balanced. The object does not stop moving. It's still moving downwards, but it stops accelerating. It does not continue to pick up speed. It just becomes locked into whatever speed it's currently moving. Section 1. So lots of different examples of free body diagrams. We could go on and on analyzing the free body diagrams of a variety of situations, but pretty much what you need to know are a couple of general rules. First off, look to see if the object that you're drawing the diagram of is accelerating or not. Remember, if it's moving at constant speed or it's at rest, then the forces on the object have to be balanced. But if the object is speeding up, then there's going to be extra amount of force in the direction that it's moving. And if the object is slowing down, then there's going to be extra force working against the direction that the object is moving. So if you think about whether it's accelerating or not, it can tell you what your free body diagram should look like in terms of the sizes of the forces. And also, as we learned today, don't neglect gravity. Gravity is pretty much pulling every object towards the center of Earth. Sometimes it's balanced out by a supporting force. Sometimes gravity is working against air resistance. And sometimes gravity is just the only force that acts on an object, especially when air resistance can be ignored. But it's always there, and we can't forget about the force of gravity. Finally, before I leave you, remember, just because an object is moving in a certain direction does not mean that there is a force going in that direction. Sometimes there is, but if you push an object or fire an object and then let go, then your force is not still with the object. The object is just moving on its own. And so there would be no force in that direction, even though it might seem like there would be. So keep that in mind as we get to our class activity the next time that we meet. Thanks for watching, folks. Have a good day.